This is section 4.1. We're going to be talking about systems of linear equations in two variables. Now, basically what a system looks like is something like this. In the last chapter, we were graphing linear equations in two variables. What we're going to be doing is we're going to be looking for an ordered pair, x, y, that I could plug in for each equation and it work. Okay, we're going to learn three different methods for solving this. And they all have their own advantages and disadvantages. Two or more equations must be satisfied at the same time. In this section, we are dealing with things with two variables, x and y. In the next section, we're going to be dealing with things with three variables, x, y, and z. Okay. General rule of systems of equations is that however many variables you have, that's how many equations you're going to need in order to get it solved. Okay, now these first couple of problems, all we're being asked to do is to decide whether or not this particular ordered pair is a solution to this system. Meaning if I plug in -3 for x and 5 for y, will it work out for each equation? It has to work in both. Not one, not the other, but both. Okay, so let's just check it in this first equation. That would be 9 times -3 plus 7 times my y is 5 is equal to 8. This gives me -27 plus 35 is equal to 8. Do the arithmetic, 8 equals 8. So it checks out in the first equation. Now, if it didn't work here, I could stop because I would know it didn't work in both. But now I need to check this one. 8x, so 8 times -3, plus minus 9 times y, which is 5, is that equal to -69? This would be -24 minus 45 is equal to -69. Combine these two and you get -69 equals -69. It checked out in both of them, so yes, -3/5 is a solution. So this will be how you check your answers once we talk about how to find the ordered pair that will work. To check it, you'll plug in whatever your x is, whatever your y is, and it needs to work in all of the equations. Okay, so let's check 8, 5 into these two equations. So 8 is x, 5 is y. This one has the y coming before the x. Make sure that you don't let that mess you up and you don't make a stupid mistake. So 5 times x, where x is 8, minus 4 times y, which is 5, is equal to 20. That is 40 minus 20 is equal to 20, and 20 does equal 20, so it checks out in the first equation. Now check the second one. 3y, so 3 times 5, is equal to 2x, and x is 8, plus 1. This gives me 15 is equal to 16 plus 1, or 15 equals 17, which is definitely not true. So it worked here, did not work here, it's not a solution. Okay, so it has to work in both. This is how we would check. So how do we actually find these solutions? The first method is the graphing method. All right, what we're going to do is we're going to use any method that we know of, any method we learned in the last chapter, to graph each line on the same coordinate system. The point where the two lines cross will be the answer to the system. If you remember from the last chapter, we said that a line is a visual representation of every single solution to an equation. So if this line represents every solution to the first equation, and this line represents every answer to the second equation, the point where they cross, that's the only point they have in common. That would be the only point that solves both. Okay? So let's try getting this thing graphed. All right, so if I want to graph x minus 4y is equal to -4. I can try using intercepts, which we did by plugging in 0. So let's say x is 0, and this is for the first one. If x is 0, then that 0 goes away. I have negative 4y is equal to negative 4. Divide both sides by negative 4, and you get y is equal to 1. So this would be the point 0, 1. 0, 1. Now let's plug in y equals 0 into the same equation. That would be negative 4 times 0, which is 0, so I end up with simply x equals negative 4. So I would have the point negative 4, 0, which would be here, which means that the first line looks like this. Okay, so every single solution to that first equation is somewhere on this line. Now let's go to our second one. I'll do this one in red. I can try using intercepts again. If x equals 0, then I have 3 times 0, which is 0, and I get y equals 1, which would be the point 0, 1, which is right here. Now we are looking for where they overlap, so this is definitely at least one of our solutions. It is possible that we have more than one. Okay, so I can't say this is my answer yet. I know this is part of my answer. I need to finish graphing that second equation. Okay, so let's try y equals 0. That gives me 3x is equal to 1, and I could divide both sides by 3 to get 1/3, which would give me the point 1/3, 0. But if you don't like having a fraction, well, I mean, if you're okay with it, you could estimate that that would be about right here, and you could draw your line. If you weren't so happy with this, you have other options here. If we have 3x plus y is equal to 1, and I move this over to here by subtracting 3x from both sides, I have y is equal to negative 3x plus 1. Remember y equals mx plus b? 1 would be your y-intercept, which is right here. Your slope is negative 3, which is negative 3 over 1. So from this point, we can go down 3 and over 1. So those are two different methods to get the same line. You can see that my estimate of 1/3 here lines up. Okay. So my answer is where the two lines cross. They cross at the point 0, 1. Okay. This is my answer. Now, how is it possible that we could have had more than one answer? If this is the graph of my first line, and then the graph of my second line was exactly the same, meaning that these two lines were the same, they were just in different forms, then they would cross at every single point on that line and we'd have infinite solutions. We're going to talk a lot more about that in just a second. But for graphing, you graph both of them on the same coordinate system. Wherever they cross, that's your answer. Now, there are certain disadvantages to the graphing method. Lines don't always cross in an easy point. They may cross at a point involving fractions, or they may cross at a point that is well off of our grid. And that just makes it difficult as humans to read them off, okay? The graphing method requires the perfect ability to graph and the perfect ability to read the point where the two lines cross. So we don't have that all that often, but we use the language of graphing in order to talk about what our answers look like or give an idea of what kind of answers to expect. Now, I mentioned the first special case. We're going to see how this pops up a lot more, but here's the basics. Two equations may represent the same line. In this case, we have infinite solutions because the lines cross at every point on the line. Only points on the line are solutions. Our answer is infinite, but it isn't everything. Do not call this all real numbers. So basically, if this is my line, and then my second line is on top of it, every single point on this line is a solution, but this point over here is not. So there are infinite points on the line, so we have infinite solutions, but it's not everything. Okay? We call this kind of system dependent and you'll be asked to complete a set written in set builder notation, and the standard form of the equation should be written in the blank. We will get to this in example. This is for reference right here. Okay, and for the next two methods we're going to be talking about, if your variables end up canceling out and you end up with something that is true, then you have a dependent system. This is mainly what we're going to be looking at in a few minutes. Okay. It is also possible that your two lines are parallel. Parallel lines never cross. Our answer is where they cross, but if they never cross, then you have no solution, which we use the symbol that looks like this. Unfortunately, because we're human, we cannot be sure that lines are parallel just from graphing them. You know, this is the empty set. That's how many answers we have. If your variables end up canceling out and you end up with something that is false, then you have an inconsistent system. Okay?